Great. So I've been given this super high-tech pointer thingy, so I'm going to try it out. If it fails, then I'll go back to the old-fashioned keyboard way. I'm Oliver Sharp, and I'm the GPM on the AGPM on the Indigo team. The Indigo product, which is actually officially known as the message bus, is something that's being built by one. What's a GPM? Wow. Woohoo! We are in a new world. Excellent. Okay. So that's a group program manager, which is one of the, basically the product units are divided up into a couple of functionalities, PM, test, dev, and all the PMs report to the GPM. Sort of my job to ship at the end of the day. Hopefully something vaguely approximating what the customer needs. So basically, the message bus team is composed of two product units, and I'm in one half of it, which we call the XML messaging team. So what I'm going to do at this talk is I'm going to give you a little context, a little taste of what the message bus is for, a little taste, very little, of the object model that you use to program it, and then I'm going to talk a little bit about GXA, which you may have heard of. It's this set of protocols that sit on top of SOAP and extend it for a variety of different distributed messaging requirements. Then I'm going to leave, and Keith is going to come up here, and he's going to tell you about the Web Services Dev Kit, which is something that we're releasing very soon so that customers can start playing around with all these protocols we're releasing earlier than we're going to ship. We're part of Longhorn, which is shipping in 2004. Okay, so let's dive in. Aha, excellent. All right, so what's the point of building this message bus? Our mission is that we want to make .NET the essential platform for writing distributed applications. So that's a fairly bold statement. But basically, we want to support a very broad range of topologies, and we want this to be a general purpose system, not one that's tuned for one specific niche kind of distributed app, but one that a whole variety of different ones can be built on top of. So we worry a lot about how to make sure that the object model that we're defining is very extensible and very flexible, and not scoped in on one particular part of this very large problem. Kind of a core principle for us is this concept of virtualizing the network. So this is probably motherhood and apple pie, but I'll go through it anyway. In the sense of virtualizing a computer, one of the things you try to do is you try to divorce from your programming model the details of the specific physical implementation of machine that you're running on. In the same sense, you want to try to write distributed apps without baking into it notions about what machine name you're running on, whether a particular service is implemented on 1 machine or 5 machines or 10 machines, because these things change over time, and if the code has that kind of stuff baked into it, it becomes very, very brittle, and any kinds of changes to the physical topology will break it instantly. So you'd like to try to virtualize the network enough so that you can be flexible at deployment time and at maintenance time in how you map that virtual topology onto a physical one. And another core value for us is this concept of interop. This is not always a core value at Microsoft in general, but it is for us. The reason why is that most of our customers tend to be enterprises, or at least that's one of our core customers, and enterprises don't have a single platform. They have lots of platforms. They love web services because it's this very flexible, plastic kind of medium where they can have different platforms talk to each other. If we went in and said we have this great web services thing for you, but it doesn't talk to anybody else, they would simply not be interested at all. So that's a core value, and it turns out to cause all kinds of trouble for us, specifically in the area of security, which traditionally has not been a domain where a lot of interop is possible. And so that means we have to have a very pluggable, extensible model so that you can take your peculiar security authentication model or your access model and apply those policies on our platform and apply those policies across our platform and other platforms. Okay, so what does it do? So basically, the message bus is this infrastructure upon which users, developers can write these things called services, and what we provide is the infrastructure and a layered framework for writing those services, which hopefully makes it easy to write those services and which allows you to exploit the various features that the platform gives you and allows you to add them to your application. So you can write a basic application, and then you can realize, hey, you know what? We really needed to add some more robust security to this application. We want to start encrypting. We want to start signing messages. We're running into these problems where there are these transient network failures, so we'd like to do some queuing. and I don't have to go rewrite my whole app in this new way because I suddenly wanted to add queuing between two endpoints that are talking to each other. Or I want to survive actual node failure, so I want to add durable queuing, and I originally thought that non-durable queuing was enough. You'd like all of these kinds of extensions to the platform, of using features of the platform, to be very seamless from the application point of view, and you just throw an attribute on your code, and suddenly you're taking advantage of more of the features. We worry a lot about content-based processing, and when we refer to that, we're exploiting a property of SOAP, which is that SOAP has this extensible header mechanism. So you can throw arbitrary headers into SOAP, and you can take a SOAP message and throw extra headers into it, and it remains a well-formed message, which has not been historically a property of most distributed application protocols. Traditionally, they tended to be fairly inextensible, and if you wanted to extend them, you had to do some fairly weird shenanigans, and often the natural way to extend them would break existing endpoints because they were assuming that the grammar of protocol communication was pretty hard, baked pretty hard. So we do all of our processing of deciding how to deal with a message by grubbing over these headers and then dispatching off the headers to particular handlers that then go implement the semantics in question. Some of the specific features we use this mechanism to implement are routing and multicast. I'll talk about these in more detail, so I won't go into them right now. Security, obviously. There's a whole major effort that we've been undergoing of adding richer declarative semantics to messaging. One of the things that you find when you start writing rich messaging applications is that you would like the endpoints to be able to declaratively state a broad range of things about themselves. For example, an endpoint would like to say, hey, you know what, if you want to talk to me, you've got to encrypt using the blah-blah-blah encryption algorithm. If I will accept the following kinds of signatures, I understand the following kinds of authentication servers, etc. So it would be nice to be able to tell somebody that ahead of time declaratively so that they can inspect, find out what you need, and then shortcut a lot of the discovery, negotiation, chit-chat that often happens at the beginning of the conversation. So we're working on that. Reliable messaging is a crucial feature for a lot of our customers. Reliable messaging basically means that the infrastructure will enforce certain properties of the message exchange, such as exactly once in-order delivery. What that means is that your application doesn't have to worry about all of the possible failure modes that really happen in the networking infrastructure because the system will prevent you from seeing some of them and will simply tell you fail rather than sending your message multiple times, forcing you to be idempotent, blah, 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 all these kinds of complexities that your typical developer would just prefer to avoid. So RM is a really nice way of not only adding reliability, which it sometimes is used for, but also reducing the set of error conditions that you as a developer have to think about. Transactions, we use that bucket to actually refer to a pretty broad spectrum of issues. There's a general problem in a distributed system where you would like multiple pots of state in the system that are in different places to stay in sync at some level. There's a lot of ways to deal with that problem. One is to say, screw it, and just have them be inconsistent. That sometimes works, but often isn't desirable. Another model which has worked really well on the internet is loosely coupled consistency with caching and TTLs on the caches. That's how DNS works. That's a form of state consistency. Then there are harder forms of state consistency, such as compensating transactions, and then kind of at the extreme, two-phase commit, full, hard consistency with locking. It's often not desirable to let another company hold an arbitrarily long lock on data in your company. So 2PC isn't always a great solution for people doing, B2B kinds of communication. But it is a powerful way to ensure consistency, so it's definitely one of the notches on this kind of dial that you can turn from no consistency to hard consistency. And then, of course, you want to be interop with the existing Microsoft platform. So that means you've got to interop with COM+ and the current .NET platform and all kinds of other interop issues, which are sort of grubby but necessary things to do in order to maintain our reasonable story to the customer. Question.
So, in your transaction story, are you saying that you will have support for compensations?
So we're currently speccing out the level of support we have. We will definitely have two-phase commit support, and we currently expect to have, but haven't absolutely locked down on a compensation story. There's a question about, would it show up in Longhorn Client, Longhorn Server? The expectation would be the more advanced support would probably be in Longhorn Server, which is a little further out. But that's an area of active discussion right now. The specs are for our shipping product in Longhorn client in that feature area will be locked down in the next month or two. Okay. All right. So that's what some of the features. Now I'm going to drill a little bit on routing. I'm going to, just to give you a sense of how I'm going to spend my time, I'm going to do routing in a little bit of detail so you get a sense of what it means. I'm going to do security in a little bit of detail. I'm going to buzz through this stuff super fast because I don't really have time to go into it in any great detail. That just gives you a very, very tiny sense of what it's like to actually write an app against this thing. Of course, you guys can't see anything I'm talking about. And then I'm going to talk about GXA a good bit and give a quick status update. And that's just kind of how I'm going to allocate the time. Please feel free to jump in, ask questions as we go along, although I may rudely cut you off. Yeah, question?
What's the difference between the reliable messaging and the traditional transactional messaging?
Right. So the question is, what's the difference, or I would say relationship, between transactions and reliable messaging? So reliable messaging historically has typically meant that there's a queue between the two endpoints, that when you throw a message to another endpoint, it'll get held in that queue for a while. And if the queue retries for some set amount of time and it never gets an ability to send the message, it will then throw an exception and say, failure. Sometimes that queue is in memory. Sometimes that queue is on the disk to survive physical node failure. Often, the reliable messaging system uses transactions internally when it durably stores those messages to a database in order to ensure consistency of itself without exposing that to the customer. A separate kind of thing is, from the programmer's point of view, I'm going to say, start transaction, blah, blah, do stuff, do side-effecting things, end transaction or abort, and if I abort, all those things get rolled back. So at the reliable messaging level, you don't necessarily expose any transactional semantics up, although you may use them internally. Now, the two are often used by the same customer, and so what you'll often find is people will say, start transaction, pull message off of my reliable, durable queue, do some processing, end transaction, so that the message processing action and the associated state changes that you make are held in a transactional bubble together. So they often work together, and one often uses the other to implement itself, but they're actually distinct notions at the programmer level. Okay, okay, so let's buzz into routing. So basically, the purpose of oh, wait. Let's actually not bother with this. I kind of covered it. So let's do routing. So the purpose of routing is that when you're writing distributed apps, it's often the case that you want something a little more complicated than node A wants to send a message to B, and it knows B's name, and it's just going to go directly to B a la TCP. Well, it's not quite fair because, of course, routers in between in TCP allow you to have flexible routing models. But from an application point of view, in TCP, you say, open remote machine named foo, and then you start talking to it. And there's no notion in TCP that there are explicit intermediaries that the application can know about and can manage. However, if you're sending messages around, you often want to have something a little bit more flexible than that. And so you want to surface some of the routing semantics at the application layer that in TCP are traditionally held down at the router level. And so here's an example where you might do such a thing. Let's suppose that I'm going to actually go over here because I've been unfairly giving you guys over here an advantage. Let's suppose that there's a client, and it's going to send a message to MSDN with the action search. Now, today, we expose subsets of a particular domain, of a particular namespace, like msdn.microsoft.com. We have to surface that up at the DNS level if we want that to control where that message goes, how that name is resolved, because DNS only allows you to resolve at the the .name level. What you'd like to do is you'd like to say have a policy which says, hey, I'm always going to go to Microsoft.com. You don't have to understand details like, well, I've subsetted my namespace topology and I call one part of it MSDN, and now you have to know about that. What you know is you can send messages to the Microsoft.com domain and they always go to the same place. But I can tell my router, hey, those messages, the rule here is I want to round robin between two lower level subsidiary routers whenever somebody sends a message to the Microsoft.com dev MSDN namespace. So that was where that message went. So this router, in this case, decided to ship it off to dev router 2. It could have shipped it to another router, but it decided in the round robin rule pinged it to 2. Now that dev router can decide where it's going to send the message. And note that in this case, we're actually using a different field of the message to make the decision. In this case, it's using the action to decide what to do. So it's saying, well, search is going to go to either the search 1 or search 2 router. So what's nice about this routing model is that you can match on any header, and you can make decisions on any header, and you can apply different policies to any header. So that's nice. That lets you build these flexible topologies and interpose routers and put all sorts of general purpose models in there. But the problem with this, well, a problem with this, is that if you use it too aggressively in the way that I put it just now, you're going to be routing these messages through all these silly intermediaries all the time when often that's unnecessary. So referral basically fixes that problem. And what referral does is referral says, hey, by the way, for the next n amount of time, you can send messages that are shaped like this directly to a different place. So to give you an example, in this case, we're doing a, well, I'm going to go to this guy again. So in this case, we're sending a download message with a zip code in it to Microsoft MSDN. And the router here has a rule which says, I happen to know something about zip codes, and I know that this zip code is physically close to a different router. So I'm going to actually send you to the Chicago router rather than having you talk to the Redmond router, which is a less optimal one. And in general, there are lots of decision metrics like this that are focused on network topology. That's what Akamai's whole business is to find the network proximate place for you to go for replicated content. So that's what this is doing. And this is a simple rule. The real rules are more complicated. So it sends you off to the Chicago router. But what the router also does is note that number 3 thing there. What it's saying is, hey, you know what? For the next some period of time, if you want to do continual downloads, then just go straight to the Chicago router and don't bother with me. And what's nice about the set of policies that we support in the GXA standards is that there's a very flexible model for sending these kinds of upstream policy notifications. And in fact, in this case, we're sending router policy, but in the fully general case, we can also send security policy. So we can say things like, the simple case is, okay, I want to talk to you. And it says, no, you can't talk to me unless you have the FUBAS token from a particular security service that you need to talk to me. You can actually propagate policies like that up. And so then rather than having to do that initial handshake where you exchange all kinds of information about each other, you can have the whole policy that's needed in order to talk to me squished upstream and to optimize the communication. The nice thing about referrals is that in the routing case, certainly, and in general, often, you can always throw them away. They're just hints. Any questions about routing, or is this all kind of obvious? Yeah?
What implications does all this have when you go into multicast?
Right. So the question is, what about multicast? So we thought a lot about multicast. There's the problem with multicast, well, an interesting aspect of multicast is that there are a set of different scenarios, and they have pretty radically different requirements. So in multicast, you've got everything from the trading floor TIBCO, multicast thing, which is exploiting IP multicast, and it's guaranteeing that the latency spread of message delivery to a bunch of nodes on the same subnet is within a certain very micro delta. That's like one kind of multicast with very hard certain kinds of constraints on it. Another kind of multicast is, I want to send this event to 1 million people, so I want to do this fancy fanning tree, and I want to compute min spanning and all this kind of fancy algorithmic stuff to try to optimize the number of actual message transfers used to send this one event to lots of people, but I don't really care how long it takes to get there. And then a third case of multicast is just the boring old, I want to send this event to a relatively limited set of people, and I like that model because it's a nice, convenient programming model for me to think about. And so we're focused on the third of those cases, which is that, hey, this is a nice programming model, so you'd like to support it in your messaging infrastructure. So our model for multicast is that you can set up a set of rules in our system for how to route messages, and you can send a message to one endpoint and then have it be multicasted out to a set of endpoints. We are not attempting to tackle the fancier and more esoteric, massively scalable multicast problem or the very highly optimized IP multicast problem. We think those are really interesting scenarios, but they're not in our V1. We're not really taking those on. Yeah, question?
I'm wondering at what level of granularity the router and referrals to the client exist. Is the router something that exists on board their machines or a group of machines?
Okay. So the question is, where are these routers, and how does routing work in the system? So the nice thing about routing in our system is that it's this very endemic property of the system. So every single process that participates in any distributed app has a router in it. And The router is the fundamental dispatcher that basically takes a piece takes a message and decides what to do with it. And sometimes what it decides to do with it is send to someone else. And there are various optimized cut-throughs so that if you're doing, intra-process stuff, you certainly don't serialize it into SOAP and all this nonsense. And if you're doing it across process, then there's optimizations you can do to avoid networking layers and so forth. But basically, we've used this organizing principle of routing throughout the system as our general means of taking a bag of bits and handing it to whichever pieces of code are interested in that bag of bits. So there can be a standalone router running on a machine that routes whole messages, and that's its dedicated function. But that's exactly the same logic, same semantics, and same infrastructure that we use to send a message between processes. Question back here? Yeah.
How high do you target to scale, both in terms of the number of machine or clients and in terms of the number of addresses there? So my question is, if you'd have 50,000 destination, how will that router be able to manage 50,000 addresses and be able to dispatch on them?
Right, so the question is, it was a general question about scalability, also applied specifically to the router. So as a general scalability goal, our goal is to support distributed apps that have as many nodes as there are nodes on the internet. So that all sounds very nice, but what does that mean in practice? Because we're resting on top of the fundamentally federated infrastructure of the net, we're using DNS and so forth, we don't have, some massively centralized server that we've suddenly created that becomes a scalability bottleneck. So the system as a whole is as scalable as the internet is generally because it doesn't have any centralized, it doesn't introduce any new centralized nodes. Now let's talk specifically about the scalability of one router. So the way that the system is designed, because dispatch is this fundamental property that is how the system works, we've spent a very great deal of time making it very cheap to apply rules to messages. So in particular, what we've done is we've taken the query language that we allow you to apply to headers. We've subsetted XPath to the part of XPath that we could efficiently implement. We have a compilation algorithm that takes that subset of XPath and compiles it into an NFA, and then it takes that NFA and compiles it into a DFA. And so what we've done is we've actually run experiments where we've put 1 million rules on a router, and the degradation of performance is, from one rule is on the order of 30 to 40%. So we scale very nicely in terms of how many rules you have. Then there's a whole separate issue, which is how many messages can an individual router handle. And that is, we're too early in the product cycle to be able to give you any hard numbers about that. Our goal is to do as well as possible, but we know that there will certainly be limits there, and so our goal is to allow you to have to have as many routers as you need and let them run independently so that you can scale using the traditional web model of scale out rather than scale up. Although we of course care about scale up as well. Is that adequate answer?
That was very nice.
Okay. Great. All right, so that's routing. So let's talk about security. So this is a subject of some compelling interest to Microsoft and its customers. What security means in a distributed environment, or actually more or less for any environment, but specifically with respect to distributed applications, is that we want to ensure message integrity. So we want to make sure that I got the message you sent. We want potentially to worry about confidentiality, so no one else can read the message. We want to worry about authentication, which is who are you really versus who you claim to be. And then authorization, which is, great, I know you sent me a message, and I know I got the message you sent, and I know no one else saw it, but now do I decide to let you actually do the thing or not? And authorization. And in addition, to kind of make the mix a little more complicated for us, we have to worry about this whole problem of integrating with existing mechanisms. It turns out that our customers are very fond of security mechanisms. We went to one, so I think my best answer so far was, what authentication server do you use? We love authentication servers. We have 43. And at any rate, in any large enterprise, they have authentication services littering the landscape because they've grown over accretion. They've got username passwords over here. They've got some, maybe they've got some, a little bit of this Microsoft stuff over here, and they've got a little bit of some stuff over here and a little custom thing over there. And if you went in there and said, we have this wonderful solution for all of your people who are based on Microsoft authentication, they would smile, nod, and kick us out the door. So we've had to define a security system which allows you to plug in any kind of security model, well, almost as many kinds of security models as we possibly could within the same framework. So in particular, if I write a web service here at Microsoft and I get some identity token from Windows, and I call my friend over at Sun and I want to pass that to my friend at Sun, that person currently, without the stuff that we've been defining in GXA, there was no way to encode that identity in a reasonable way so that they could look at it and have confidence that I really was vouched for as being who I am at Microsoft. So WS Security, how many of you guys have seen, read about WS Security, know basically what it is? Some of you. Okay. So WS Security can be thought of in a lot of ways as an encoding scheme and an exchange model for taking certificates that exist. We didn't define any new certificates. We just said, oh, so you have an XRML token, or you have an X509 token, or you have a curb token, or you have a this or that. How do you take that thing, that blob of binary bits, and encode it so that you can send it over to somebody else so that they can use it? So that's one of the fundamental problems that security was trying to solve, is just how do you do the encoding problem. And then on top of that, you have to start defining semantics of how you exchange these things and how you manage shared trust, so that when I get a message that says you're fubaz@sun.com, we have some way of making sure that the Sun identity server that I know about really did vouch for you, honest to God, and that you didn't just make that up. So there's a whole collection of standards which allow you to do these things in a federated way. So what do we build? I'm going to talk a teensy bit about that in the end of the deck, but let me just talk about what we're building first. So a way to think about what we're doing, and I guess I owe you guys the next one, right, is that we provide in the message bus a set of canned features around security. You don't have to use them. If you, as the app writer, want to go roll your own security model and do your own tokens and paste in your own custom headers and use your own servers, that's fine. We're not going to stop you from doing that. But what we did was we built a bunch of infrastructure that we think a lot of people will find meets their needs, and we're supplying that with the system. So in particular, we let you define a security configuration. So configuration is stuff like, well, I understand the following kinds of encryption models and the stuff I was talking about before. I understand these encryption models. I'm willing to accept the following authentication tokens, ... And then we have a management piece which allows you to take those policies and stuff them in a cache. And it allows you to go get licenses or credentials and stuff them in a cache. So your policy might say, every time I as a service reply to a message, I stamp it with my cert that says this is really who I am, so that the client at the other end can tell that I'm the one who sent it. And the policy might also say, whenever anything comes in, it better be signed by a signature that I accept, and it'll be verified as it comes in. And if a message comes in that violates that requirement, it gets thrown out. And so the app, the nice thing about this from the app's point of view is it doesn't have to think about these things. It just announces its policy, and the infrastructure enforces it, and any messages that violate that will be thrown away without your even having to think about them. So that's kind of a nice model that most of our customers want. They really want to have a way of making assertions about security and then mostly not littering their code with a lot of details about it if they can. Question? Okay. Another thing you want to be able to do is you want to be able to create these credentials and manipulate them. You want to be able to sign things. So signing is actually kind of an interesting problem. If you haven't dealt much with XML and SOAP and so forth, one of the things about a signature is that typically the signature algorithms require that exactly the same bytes be in exactly the same order when you compute the signature, and that's how it verifies it. And that seems sort of obvious. But when you have a bunch of headers, well, what happens if somebody in the middle of just threw a header into your message? Well, how are you going to know that the two signatures really matched? Because they won't match if you do the sort of naive comparison. So one of the things we had to do was define this very rigid canonicalization algorithm, which says when you get a message, you pass it through this kind of grinder, and it comes out the grinder, and then you know that that thing is what was signed on the other end, so you can do the verification. So that's a sort of a piece. And again, we don't want to go inventing algorithms or inventing signature models or any of this stuff because there already are well-defined ones in the industry. So what we did was we basically said, here's how you use the existing pieces to build a policy up that's uniform across systems. Okay. So let's see. All right. So just a quick sense of how security might work. Get some over here now. The client, let's say we're going to build a client, and it's going to call this credit check service over here. Now, the credit check service wants to make sure that you have the right to call it. So it insists that you pass it an XRML license which says you have the right to call it. All right, well, where do you get one of those? Well, you get one of those from this license service up here. Now, what the license service does is when you walk up to it and you give it an identity token, it looks up in, say, an ACL list and says, yep, you have this right, so I'm going to hand you this license. Okay, well, where did you get the identity token from? In this case, we went to Passport and got a curb license. This is in the near future, but not in today's world. And you went to Passport and you got a curb license. So what's nice about, there's a bunch of nice things about this factoring. One thing is that you can outsource, right? So you as an org don't have to run Passport. You can use Passport. It can pass you back a credential in a form that you can then use with other companies. You could outsource the licensing service. You could put the licensing service on a farm of machines. Another thing is that XRML license that you get back can say, hey, this license is good for the next 20 minutes. And so now I can make hundreds and hundreds and hundreds of calls to credit check at the price of one call to licensing service. So you can make a decision as to the window of that you're going to leave open in terms of revocation, right? The problem with having a TTL is that you have the revoking problem, which is, oh, wait, no, I want to revoke your license, but now I've given it to you. How do I do that? And the answer is, well, when you set your TTL, you're announcing, I'm willing to live with this revocation problem for the next n minutes. And in some applications, you want the number n to be 0, right? So in some cases, you don't want to have any kind of a revocation window. And then you just eat the cost of building a scalable system that can take all of the authentication requests constantly, versus some cases where, a day even, or a week, or it might be okay, or certainly 10 minutes might be fine. So the application can make a decision as to what kind of policy it wants, and the infrastructure is flexible enough to support both. All right, so let's look at another scenario. Suppose that you're McAfee. So you have this interesting problem. Every now and then, your customers really want their latest signature file right the hell now. And they don't want to sit around and wait. They want it right now, and they all want it right now because, NIMDA hit or something. So you have to think about running servers that are sufficiently powerful to support every one of your customers hitting it simultaneously, more or less. And then most of the time, your servers just sit there completely idle. So that's kind of an undesirable situation. Now, there are companies whose business model is to run thousands of servers, namely Akamai again. So wouldn't it be nice if you could let them host the files on their machines, which are already set up for this sort of thing, and you could only do the authentication handshake? The other thing is you don't really want to tell Akamai who all your customers are and which ones are premium customers and which ones are second-tier customers. So you'd like to not tell Akamai who's visiting them, and you don't want the ACL list to all live at Akamai, but you want the actual files to be hosted there. So this factoring model lets you do that. In this case, what's going on is you could go to some authentication service. We use Passport again, but it could be some other one, or it could be something hosted by McAfee. And then once you've got that token that says who you are, you can go to an admission service. In this case, we've added another wrinkle, which is that we've added a role sense. So we've said, okay, some of our customers are top-tier customers, some are medium tier, some are low tier. So what you can do is you can go to Passport, you can get a license, you can go to the admission service, and it says, yep, you're a top-tier customer. So now you got your I'm a top-tier customer thing. Then you can go to the permission service and say, hey, as a top-tier customer, I want to go get my license, my signature file. You get back a license that says for the next 10 minutes you can download that signature file. And now you can go out to one of these hosted servers out in the world and get your file. So again, we've got nice privacy here where we can prevent the subsequent conversations from knowing what went on upstream of them. We've got the outsourcing option, and we've got a very nice scalability model. So what's nice about this approach to the problem is that it's very flexible and allows you to implement a lot of different topologies for the system. Any questions? Okay, cool. So we've been working a lot with the Passport team. Some folks on the Passport team co-authored the WS Security spec with us, and they are working to support this directly so that right now what we have to do is we have to get the material that comes back from Passport and grub over the bits and generate a GXA token for them. They're going to go do that work, which we'd much prefer them to do, so that they actually just hand the GXA coded license back directly. We've been doing the same kind of thing with Windows. So what we'd like to be able to do is say, okay, go to a Windows box, get a token, pass it through different firewalls, different orgs, different platforms, whatever you want, then make a function call back to the original place and pass that token back, and then you can apply the authentication rule when you get back there. So we're working with Windows to get them to encode their security model in this same way. And again, some folks from their team co-authored the spec as well. So the whole effort was kind of this mutual shared effort across the company. And we've worked with actually some people from MSR as well to try to make sure that this is a well-founded security model. And now, since then, we've gotten IBM and VeriSign to co-sign it. BEA is signed on, Sun signed on. So we've gotten this thing has now gone from a little sort of kitchen cabinet effort to being this fairly broadly shared consensus across the industry about how you do a factored security model, which we're really psyched about. So that was a fairly monumental amount of work. OK, so I promised to give short shrift to this. I'm going to give even shorter shrift than I thought I was. But I'll give you just a very, very tiny flavor of it. So I've been talking about what you can do with the system. Now I'm going to talk a little bit about how it's actually built. So the way that the system's built is that there's this low-level piece, which is a bunch of infrastructure about how you communicate and how you deal with transports and so forth. A messaging framework that sits above it, which allows you to think about the world in terms of endpoints that you're going to send messages to. That's a fine level for some developers to think about, but a lot of developers don't really want to think about it that way. What they want to think about is, well, there are these services, and I talk to services directly. So they don't want to worry about, the message objects and encoding messages and adding security managers to them and, having ports and getting connectivity and all this kind of complexity. So this is a higher level model that we're providing that sits on top of the messaging framework. And if you don't need to know the details down at the bottom, you can live up here in this kind of higher level model. But it's all consistent. Of course, the service framework is fully built on top of this. So if you need to go down, there's nothing. It isn't like a shift in model. It's just a different, a lower level of abstraction. And then above that, our apps and also custom tailored frameworks. So for example, if you want to write a distributed storage system, you'd like to be able to still leverage, the same queuing, the same security model, the same everything else. And so we want people to be able to extend the framework to add domain-specific classes to it and then put apps on top of that. OK. So this is a very trivial kind of top-level processy diagram where you're basically I'll switch again. Where you're basically going, it's very similar to the IS6 architecture where you have this thing called a listener which owns the wire. And when a message comes in to that listener, it has to decide where to send the message. If it doesn't know any better, it can send it to this general purpose manager, which we're calling the process manager here. And it's up to the process manager to know how to dispatch that message. In typical cases, what it does is it goes hunting around through the system to find the app that wants that message. It spins up a worker process for that app to run in. It spins up that guy's app domain. And it spins up an instance of some code inside that worker process, and then it hands it the message. So this is very, very similar to how IS6 works. And the other thing that happens is once this worker process spins up, it can go tell the listener, hey, you know what, for subsequent messages to my namespace, don't bother the main guy. You can go ahead and send it directly to me. So that's a nice optimization. There's another optimization that you can do, which I didn't put on here, which is if you really wanted to, this app could actually open up a custom port, and you could start talking directly out the port from this app to the other side, which in some cases is feasible. And that further eliminates the kind of intermediaries. So our goal is there's a very flexible model that you can route the message through all kinds of intermediaries to get to its endpoint, but then there are levels of optimization to strip away all those intermediaries so that when you're operating in steady state, they're gone, or they're out of the picture. OK, so let's see. I'll talk for a sec about these. So listeners, I already basically said this. For TCP-based protocols, which is the preponderance of what we worry about, they own a port and register for namespaces. And the goal of our layered model is, if you look at transports vary pretty dramatically in terms of their fundamental abstractions of how they think about the world. Some are symmetric, some are asymmetric, some stream, some packet. So our goal was to define an abstraction layer that would abstract out the pieces that we didn't need to worry about so that when you deal with transports, you can think of them in a uniform way. Obviously, any such abstraction abstracts away some very key principles of those transports. So if you need to, we have cut-throughs that let you get down to the more direct features of the transport that are obscured by that API. But for the typical developer, that's not really a problem. Yeah, question?
So in the multi-user scenario, how do you control that processes from different users do not conflict on their namespaces?
Right. So the question was, how do you enforce that different apps don't have namespace conflicts? There's a variety of ways to do that. The way that ASP.NET and ASMX today do it is that there's a file system, and there are virtual roots, and you can only have a particular name can only point to one virtual root, and there you are. That's probably, we will support that model. We may support another model. And of course, you can always go register yourself for a part of the namespace. But that is a very simple way to enforce it. And that customers like it because it's easy to grok. Question? OK. Oh, yeah?
So what if you wanted to actually have multiple instances handling the same namespace?
Sure.
So to distribute the work across.
Right. So the question is, how do you arrange that different instances are all implementing the same part of the namespace? So there's different places you can enforce that. There are some people who have been interested in having that be true on a single machine, so that there's different processes that are handling the same part of the namespace. So Apache, for example, uses that model. There's also another way you can do that, which is that different machines implement the same part of the namespace. That's a little more common. Well, it's also common for farms, for example. So the way you would approach that is basically that the rules in the router will allow you to do things like round-robining between different endpoints. There's a certain fundamental conflict between that model and sitting on a port and owning a port. So typically what happens is that for the duration of a particular conversation between two instances, you are less interested in multiplexing that conversation, typically. Right? That's the model with behind, say, Keep Alive in Apache. And so in that case, it's pretty simple. You just have the dispatch that decides which of those pieces is going to get triggered happens at the router level. Also, another point is that within a particular app domain, there will often be millions of instances that are all living on the same namespace. So within an app with a single app domain, that's an extremely common scenario. So for example, I'm managing POs. Every PO is its own instance. So the PO gets wired to a particular app. That app will then fire up an instance to handle that particular conversation, and then that conversation will happen within that instance. So you can do it within the app domain. Whoops, did I just change it? No. Okay. You can do that within an app domain. You can do that across processes on a single machine. You can do that across machines, and the mechanisms you use to do that are a little different, but you can do it in any of those layers. Question?
So for the namespace, does it require admin to configure the permission of different namespaces for different apps?
Right. So the question is, how do you adjudicate security policies for apps? There's a couple different ways to do that, as they are in today's stack. One way, the most common way, is that each app has config associated with it, and the app config states security policy. And typically it states it in an overriding model. So there's like enterprise-wide config, there's machine-wide config, and there's app-wide config. And whatever you don't assert about, you just inherit what's comes to you from that inheritance stream. But you can then override that with assertions in your config. So that's one way you can do it. The other way is you can do it with code. Right? The security manager is an object, and you can instantiate it, and you can whack away on its properties and set things up in it and stuff it in your channel and do all kinds of things like that if you want to customize your security policy with code as opposed to config, although most people prefer config.
So I see this is an easy problem on the server because you have a well-defined namespace. You can do it. But on the client machine, for example, two users through terminal server, you can log onto the same machine. One user might run an app saying, hey, give me all the messages that arrive at this machine. Mm-hmm. In this case, he could possibly see IM messages sending to the other users. Mm-hmm. How do you prevent that from happening?
So the question is, how is security enforced on a particular machine to prevent a malicious user from grabbing all the messages on that machine? So this is an instance of a general problem, which is if I go into your office and I splice your networking cable and I stick my sniffer and my machine in the networking cable, I can cop all your messages too. So our model is that we assume that all messages that arrive to us off the wire are completely untrusted, could have been arbitrarily screwed with, messed with, rearranged, spoofed, hacked, tweaked, etc. all security that you care about must be enforced end-to-end at the app level. And so if you want to prevent that from happening, then the sending app would encrypt the message for the purpose of the particular target app, and the target app would be the only one who could read it. You could get the message, but you couldn't do anything with it. Yeah, question?
Can I discover what services have been registered in that part of the namespace?
So the question was, how do you deal with discovery? Discovery is a very broad problem. It applies to discovering services within an enterprise, discovering services within a particular machine. So we have a set of different discovery protocols and approaches that range from the sort of UDI-ish directory in the sky kind of a discovery problem to I know there's an endpoint, now I want to find out what it can do, which is what WSDL and WSDL basically let you do, to now I want to walk up to a node and I want to have some well-defined place to go find out all the currently running services that are being advertised, and there's a notion of that as well. So there are a series of discovery mechanisms that allow you to find things. Questions? Okay. Transport adapters. Well, just buzz. I'm not going to have much buzzing left. Okay, so a transport adapter is the thing that takes the bag of bits off the wire and turns it into our abstraction or our message object, which is what we use to in the system as our internal data structure. And transport adapters are designed to be pretty easy to write because a lot of our customers actually will do this. A lot of enterprises, for example, have their own custom weird messaging infrastructures that they have internally, talk to mainframes, to talk to each other on custom networks and funny things like that. So we wanted to make it easy for them to take a bag of bizarre bits in whatever format and turn them into a uniform format that you can then write code in our system to apply to it. So that's basically the only thing. Yeah, question?
What is your position or whatever on the size of the messages?
Right. So question is, what about message size and what's our position on it? So message size is a really fun and interesting area that people get all excited about. We have spent a lot of time talking about that. There are very grave implications in terms of performance, throughput, queuing, buffering overhead, blah, 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 if you don't bound the size of your messages fairly carefully. On the other hand, it's a bloody nuisance for your applications if you have to think about these silly message size bounding problems. Another issue is that, as anyone who's looked much SOAP knows, SOAP is pretty wordy. And so another whole issue is if you can try to squeeze the SOAP messages down so that they sometimes, occasionally, always fit within the MTU of your network to dramatic, because there's kind of a cliff at the MTU in terms of perf as soon as you start chopping messages up into multiple packets and doing retries and buffering and blah, blah, blah. So we've spent a lot of time worrying about that. Our basic model is that we want the programming model not to enforce a particular message size and the infrastructure to, if necessary, chop messages up into pieces and send them as pieces. You as an engineer should know that if you insist on sending the Titanic DVD around on your network and you do multicast on it, that's likely to do unfortunate things to your network bandwidth and throughput. We argued a lot about whether we would try to write optimal performance cut-throughs for using the GXA stuff to do session initiation of long messages and then do customized, specialized, optimized stuff for long messages. We're not doing that in V1. We're not going to prevent our customers from doing it, but we're not going to try to implement that in V1. So our model is we'll chop messages up into reasonable sized buckets and send them as buckets, much the way that TCP does, except our buckets are bigger. Yeah, question?
How do you handle, it's probably related to the previous question, how do you handle concepts like virtual connections, in-order delivery, session state, streaming?
Uh-oh. So I just got asked this hyper open-ended question, which I'm not going to answer. But if you want to send me an email, I'd be happy to answer. I only have 8 more minutes before I start eating into Keith's time. So I'm just going to not answer that. Okay. And I'll probably stop answering questions in general. All right. So let's talk about so all of the stuff that I was talking about before was how do I get a message into an app? And this thing is great. I hadn't actually done any work yet. All I'd done was shovel stuff around and apply security to it and so forth. But I haven't actually gotten it any user code running yet. So once you get a message into an app domain, we have a bunch of abstractions which say, such as a port, and ports are abstraction for how a piece of code talks to the outside world. So all talking to the outside world happens through ports. And then once something comes in a port, we apply the filter engine to it, which has that optimized dispatch algorithm I was talking about to answer your question. And it calls a bunch of handler routines to apply to that particular message, and those handler routines will implement things like security and referrals and routings and so forth. And once we get through the handlers, we then hand off the message to somebody. That somebody might be sitting on the port. It might just like be blocked on the port waiting for a message to come in. There might be a queue attached to the port, in which case we throw it in the queue and then it gets pulled out. Or what's often the case is that it's destined for a particular service, in which case we do a bunch of dispatch and concurrency management at the service layer to get that message to an appropriate instance with a bag of state, a thread, and a stack, and a system stack for it to execute on. But that's a horrendously abbreviated view of this, and I'm going to have to stop there, I'm afraid. So I'm going to actually skip all this stuff and go to GXA, because I did want to cover that briefly. Okay. All right. So what's this GXA thing about? So I'll start with the part that you guys don't care about. Sorry. The business goals. So basically, the purpose of the GXA architecture was to get Microsoft out of a really sticky situation that we were in, where Sun and the J2 community had managed to define this notion of standards-based and interop around APIs, which was a game we aren't going to play and are never going to play. And so what that meant was that for a while, Microsoft was the doesn't implement standards solution, and J2 was the does implement standards solution. So that was a pretty unacceptable situation. And so our goal was to convince people that the interesting thing to standardize is not the APIs, but the wire-level interop protocol. And that effort has actually been quite successful, to the point where now it may sound even kind of dumb that this is an issue, but I assure you that when SOAP came out, it was very much an issue, and it is a huge victory for this company, and that the industry has accepted this model of interop as opposed to the old one, and we can now actually go in and credibly talk to our accounts and say that we are, in fact, very aggressively embracing and driving standards forward, which is the case. Okay, so enough blather about that. So what is GXA? It's a bunch of standards that extend SOAP into areas where you want additional semantics in order to write rich distributed apps. So for example, SOAP says I can invoke a method, more or less. But it doesn't say anything about security, doesn't have any notion of authentication, doesn't have any notion of encryption, doesn't have any notion of reliability, doesn't have any notion of multi-path routing through intermediaries, doesn't have any notion of queuing or transactions or any of that stuff. And it turns out that you can write some apps on raw SOAP, and that's fine, but you do an enormous amount of work, and that people who wanted to write real line of business apps or sophisticated apps on top of SOAP ended up reinventing the wheel a lot. And furthermore, they ran into a problem, which is great. I went off and implemented a security model, nice for me, but now I want to talk to your service, and you implemented a totally different security model, and they don't talk to each other. So these are the kinds of things you really do want to standardize, so that people don't go off and invent different stacks that don't know how to talk to each other. So the goal here is that we want to license these things for broad adoption. They should be platform, language, and implementation independent, and they should all be submitted to the appropriate standards body. And we've actually been pursuing that pretty aggressively, as you'll see in a second. So what are the axes of GXA? Well, there's kind of core messaging, like routing and so forth. There's discovery, to address your point. There's, and metadata is actually in there, which is kind of an uneasy combination. I should probably have a separate metadata axis. There's security, reliable messaging, and transactions. So these are kind of, spokes in the GXA wheel, if you will, although that's not a wheel, but whatever. And we're working on all of those. I'm going to skip this. Okay, so I'll talk about each of those different chunks for a second. So in core messaging, obviously there's SOAP. Dime has gotten a fair amount of momentum now, and Dime is basically sticking attachments into a message. How do you stick binary attachments in? Routing is and referral I talked about in some detail. Those were submitted jointly. Those were published jointly with IBM and have not yet been submitted formally to the standards body. But we're working with them for another update on routing to incorporate some of the later work in policy and so forth. Then in discovery and metadata, we've got WSDL, which basically is how you define the type, the method signature of your service. UDDI, which is the directory in the sky that allows you to go walk around and find what services exist in the world. Inspection, which says, great, I know of a service, but how do I find its WSDL, effectively? And then policy, which is a really active area of work right now, which is this general problem of how do I describe policies that are going to apply to messages and shove them upstream in the messaging stream so that people who want to talk to me can find out what my policy is and shortcut the conversation. And then contract. And then contract is actually this very cool idea. I think probably a lot of you are familiar with Greg Meredith's espresso work. I don't know. Raise your hands. Anybody know about it? Oh, no. Okay. Not very many of you. So basically the idea here is that when you look at a distributed app and you look at the messages that it exchanges between endpoints, there are very well-defined rules about what order those messages have to go in. And so you can capture those ideas with a declarative semantics, which in Greg's case were based on pi calculus. And the nice thing about that is it's a very simple grammar for doing composition and for capturing a fairly rich but constrained set of message flows which you can reason about in a nice abstract way. And so what we're trying to do is we're trying to take the semantics of the pi calculus, express them in English, and allow you to put them into endpoints as declarative statements about what this endpoint requires in order to communicate with other endpoints. And it's actually a very cool idea, and we hope that what will allow users to do is to build up semantics in like a graphical tool or with attributes on your messages, compile those into these actual assertions which are placed into the endpoint declaration for you and then can be enforced by the infrastructure. So it's pretty nifty stuff. Okay. So security. So security's got a bunch of different pieces, which I won't talk about in detail. But if you want to read about them, they are described in endless length on the website, which I will talk about in a second. And then agreements. So agreements we're using as the bucket for reliable messaging and transactions, which, as we discussed in respect to the earlier question, have a relationship but are distinct. Okay. So what's been going on? We also created this thing called WSI, which is an organization, industry consortium. It's got 300 members or something now, which is designed to have a forum where all of these companies who are interested in web services can come together and can make sure that their stuff works together. And then we also have created what's intended to become a regular semi-yearly or, well, hopefully not quarterly, please God, but anyway, a regular event where we bring together hundreds of people from the industry to present them our GXA ideas and what we're up to. And we've had a couple of those, one in the US, one in Europe, and I think they've been really successful events, getting people excited about what we're doing. So if you want to find out, status. Okay, I guess I should tell you where we are. We're in M3, and we expect to have a couple more coding milestones, a couple of betas. Our next milestone coincides with PDC, where we're expecting to release preview bits of the message bus so the customers can play with it. And we are RTMing in 04 with Longhorn. We're also hiring actively for test. My test manager asked me to put that in, so I don't know that this audience is quite the right one for that, but well, we will essay. All right. So in terms of resources, we have a website, Indigo, which has a pretty large amount of material on it. We also have a subset of that website, which you can get to directly through GXA, or you can just get to it through Indigo, which has all the GXA specs, what they are, what their status is, who their owners are, where they are in the standards process, links to the drafts of the specs. It's a fairly mountainous amount of status information about GXA, and it's all kept quite fresh. So you're welcome to go there and find out about it, and it'll tell you who to talk to participate. And that's it. So let's see. I have, it's right on the money. So I'll answer one question, but it can't be as open-ended as that one was. Okay. Yeah.
What about eventing?
Question. What about eventing? So we spent a lot of time thinking about eventing. We have decided that we're going to support a basic form of multicast. We have written a WS eventing spec, which captures how to do subscription and so forth, those semantics at the protocol level. And we're trying to figure out how much of that we're going to be able to support in V1. I think the betting is that we're going to support basic eventing and basic multicast, but not anything terribly elaborate. It's one of those things that you'd love to do, but you got a lot on your plate. So, and I guess one more question. Yeah.
What about message priorities and out of bandwidth communication?
Okay. Question is, what about message priorities and out of bandwidth communication? So let me talk first about. Well, I can talk about priority, but first you have to clarify your second part of your question.
Sometimes in a distributed application, you'll be sending a bunch of messages, and some event will decide that all those messages I'm really not interested in. I want to send a global message ahead. Destruct all my last messages.
Right.
But if they're in order, it's
Yep. So the question is, how do I send preemptive metadata assertions to affect how the application is going to process a set of potentially intervening application-level messages? Is that a fair recap?
more or less.
Okay. So the answer is that those are great scenarios. We love those scenarios. We've thought at great length about those scenarios. We've written some fabulous white papers about those scenarios. We're not going to do anything about them. Prioritization turns out to be a real bugger, given that there's absolutely no QoS support in the core TCP infrastructure of the internet. And so trying to do prioritization above a framework that fundamentally doesn't support it is just hideous. So you could think about doing some stuff on ATM, blah, blah, blah. But basically, we decided we just can't take that on in V1. In terms of the out-of-band issue, you are welcome and free to implement that yourself at the app level, but we are not going to support that model, except that there are some such messages that are supported in the basic infrastructure around RM. So reliable messaging, for example, does take a little bit of use of out-of-band messaging to send metadata around, but we're not exposing that mechanism at the user level. If you want to do that, go for it. Okay. All right. I'm going to hand it over to Keith. Thanks for attending, and hope that you are finding it useful.
Thanks, Oliver.
My name is Keith Ballinger. I work for Oliver. I'm the program manager for, it moved already. I'm the program manager for what's called the Web Services Development Kit. The idea behind the Web Services Development Kit is that while we do have the message bus plans and we do have it's really great technology being written, we've already gone to market, gone to various standards orgs, published to MSDN, had many press releases, marketing releases, so on and so forth about the GXA. And we've released version 1 of Web Services. So what we've decided to do in the interim between now and when Longhorn and the message bus ships is to do these things that we have. I've lit these different points on the board, which is basically demonstrate our leadership. Demonstrate, build up our team, and also get to our customers some of the benefit, in some cases quite a bit of the benefit, that the GXA and that Web Services offer. And so we've done that by taking a nice grand mission statement and putting the word now on it. And the idea is that we're going to take version 1 of Web Services. We're going to take ASP.NET Web Services that you have with .NET and actually any managed code web service infrastructure and allow you to do the 80% case, or maybe the 40% case, depending on what it involves, of the GXA specs. So for instance, WS Security allows you to do message-based security. While we don't necessarily implement all of the other security specs, we've implemented WS Security and allow you to do major pieces of that. So the idea is to get in the game now. It was quite infuriating. It was quite uneasy to see us releasing these specs, such as WS routing, and then seeing our own customers implement them and ship implementations before we did. We want our customers to get the benefit of these things. We think they're great. So the idea was, well, let's build a toolkit. Let's build something that's supported that people can actually use in production. Let's get it out this year, and then let's move forward. So in the first release, we're going to have multiple releases of the Web Services Development Kit. In the first release, we're going to focus on two major things, the GXA building block specifications. So version 1 of the .NET framework has support for all the various XML technologies like XML and Schema. It has support for SOAP. It has support for WSDL. What's missing, of course, would be things like routing, the ability inside of a message to identify who the target of the message is, what the intent of the message is, the path of intermediaries to follow to send the message. So that's what WS routing gives. So we've added support for WS routing to V1 of Web Services, and then we've added security. Specifically, we've added the ability to sign messages to determine they haven't been altered. We've added the ability to encrypt messages, the body or pieces of the headers, and we've also allowed you to attach arbitrary credentials and given specific support to things like username credentials and X509 certificates. Now, security on its own is not very interesting if you're only using HTTP and doing point-to-point. So one of the things we've done with WS routing is not only do we allow a client sender, somebody who's building a client that sends messages for web services, to specify the path to send a message through, we've also allowed you to build intermediaries, which you really couldn't do with V1 without a lot of pain, that you could use, for instance, flow a message through a firewall or through some kind of proxy, such that you may have the message go through multiple hops and the response may be done days later. So we wanted to enable those kinds of scenarios as well. So like a lot of toolkits, like a lot of SDKs, things like that, we have documentation, samples, a class library with the core functionality, various tools that we're working on as well that you can find in the WSDK. The schedule at this point is very aggressive, but we do feel we can meet it. We've been working on it now for a few months. August of this year, we're going to release a public beta. And then in October, late October, we'll release version 1 of the WSDK. The idea is that as soon as we have internal access open, which will hopefully even be before this beta, that all of you can start playing with and actually trying GXA-like functionality with your web services. Yes, question right here.
Do you support the May release of WS routing?
Yes. Yes, we support the we support the most recent release that was co-authored with IBM, which I don't know if actually is public yet. I believe there's versions. The last public version I believe was last September or November of WS routing. That was Microsoft only in name. We've actually coded to the version that Microsoft and IBM have worked on together because we feel that will be the interoperable one. And one of the things we're already doing, for instance, something I'm going to spend most of next week doing, is working with IBM's people on their Apache project, various people on IBM Research who are contributing to WebSphere or just Apache in general for GXA-like functionality. So beyond these things, we've also, for instance, beyond the list here, we've also implemented Dime and whatnot as well. Yes, please. The question is, do we plan to release source? The answer is no. We don't want to set customer expectations that the message bus or the framework would be in source release or message bus, and so certainly we're not planning them to be source release, so we didn't want to release ours as source either.
At least internally to Microsoft, within Microsoft?
I can't. The question is, internally are we releasing source? I don't actually know. We've tried to create as extensible an architecture as possible such that people can plug in things wherever they want to mitigate not being able to release source. Whether the source is available internally or not, I just don't know what we'll decide on our plans there. Right now, it's not. So we expect to have, and this is a typo, we expect the V1 release to be in October, and we expect the V2 release to actually be next spring. What we're trying to do here is create a lot of momentum. There's a lot of GXA specs. There's a lot of really advanced functionality that you could expect to see us implement. We're taking bite-sized chunks and we're getting them out the door. And I'll show you some demos a little later in this presentation that show that. So the idea is that we're going to release a supported product this year by October. And 6 to 8 months later, we'll release a V2 of it with additional more features, especially as more GXA specifications are released. The kind of customer we're targeting, our kind of Pry 1 customer, if you're familiar with the Visual Studio identifications, is what we would call an Elvis, an advanced developer. He's not a Mort VB user, not very, he's not entirely inexperienced. He's not necessarily an Einstein who has a lot of very advanced experience, but he is an advanced developer who's used web services in the past. For that reason, we've decided to come up with a very flexible API at the cost of just doing a lot of things by default, for instance. We're looking at longer term, we can work on those things, particularly message bus will work for all kinds of developers. We do give a lot of support for your kind of typical VB corporate developer. But for both sets of customers, we're looking at the C#, the VB.NET guy, the managed developer. We're not supporting native code. We're not supporting ATL, that kind of thing. It's purely a managed SDK. So the customer scenarios in V1 we're looking at, the real Pry 1s for us are the ability to sign messages, the ability to route messages based on various contents of headers, and the ability to decouple your network topology. So we have a referral cache that we use to actually determine where to send messages based on the name you give us to send a message to, as opposed to just to opening a port and sending it to the exact name you give us. This kind of virtualization of the network is one of the keys that WS routing gives you. It's one of the nicest things it does, because all of a sudden you can change your network topology on the fly without redistributing your app. And so that's another scenario that we thought customers could get use of right now, even with a small migration from V1 Web Services. Kind of probably two other things you'll be able to do. You'll be able to do firewall traversal. In B2B scenarios especially, customers are already doing this kind of thing. We want to make it easier for them to send messages from one company to another, traverse firewalls, do all the right security things. And of course, we allow for encryption. So you can add to this list things like file attachments with DIME, the ability to, so we have already content-based routing there. That's pretty much the large set. We allow people to do customized filtering of messages, to do their own kind of GXA-like stuff to messages. We also allow people to decouple themselves from the request-response nature of what we built with ASP.NET Web Services, where you can just send a message and you don't have to worry about there's a response coming right away. We've given some support for that. That's kind of a Pry 2.5 scenario that certainly does work now with the WSDK. Our dependencies are fairly straightforward. We work on top of version 1 of the .NET framework. And if you have Visual Studio.NET, that includes the framework as well. We don't replace core functionality. And in fact, what we've done is we've taken the lowest level extensibility point that exists in the .NET framework today and plugged ourselves in there, which is web requests and HTTP modules, in order that if you want to build your own custom managed SOAP implementation, you could still gain the benefit from the WSDK, and it would work for .NET Remoting as well as .NET ASP.NET Web Services. Yes, question right here.
So I didn't see reliable messaging in there. Is it going to be in V2?
The question is, you didn't see reliable messaging in the list on this of scenarios here or in the features. Indeed, we're not supporting reliable messaging in V1. We hope to have some kind of sample that shows how reliable messaging works. It's likely to be, or some piece of reliable messaging is likely to be a V2 feature. Reliable messaging is actually a very large feature set. You have durable reliability, where it's at least at once. We'll make sure it happens. I'll spend days trying before I give up, kind of thing. And then you have, hey, somebody got a message out of sequence. There's various levels of RM. We'll support. We haven't done a lot of work since we've been focusing on V1, but in the analysis we've done for V2, it looks like the kind of thing we want to offer. So definitely, yes, we're thinking about it. By plugging in at these low extensibility points, and by actually abstracting our architecture away from any particular transport, similar to the way the message bus has thought about things, we actually allow people to kind of, if they have a stream-based or even a DOM-based, any kind of XML-based SOAP infrastructure, they can kind of take the WSDK and we can do things to messages for them. So it's really easy to use, especially for people who've decided to take and build their kind of own custom SOAP engines in V1. The idea for our compatibility with Indigo, with Message Bus, is when Message Bus ships, we'll interop with the last release. Our last release of the WSDK will interop with Message Bus, and then we'll see whether there's a reason for the WSDK to continue to exist. We're not going to guarantee any kind of programming model interoperability, and we're not even sure between releases how much interoperability we'll offer, because the GXA specs are changing so much. So for customers who need a very, very stable platform, the WSDK may not always be the right solution. For customers who need advanced functionality, it certainly makes a lot of sense. We're planning on web releasing on MSDN. We'll have CDs for magazines. We'll try to bundle with other products where it makes sense. We'll give them away at events like TechEd, XML1, those kinds of things as well. So you should expect to see the Web Service Development Kit a lot in the news and giveaways, things like that, magazine articles toward the kind of the end of the year, from fall on. So what's the programming model? That kind of all the slides we've gone through so far have talked about. Here's this thing. It's called the Web Service Development Kit. Here's what we're trying to do. Specifically, though, we have these low-level extensibility points where we do things to messages. Given a message, You can tell us to sign the message, add some credential to the message, add some routing to the message, send it to a virtual address, etc., and so on. And then we'll do things to the message. We kind of built a pipeline that does things and then sends it on its way. And we've done the reverse as well. Given a message that we've just received, we can extract bits and pieces of it and then hand that to the developer as a nice object model. Hey, here's your, here are the credentials, the security tokens that came with the message. Here's the referral messages that came with the message. Here are the file attachments. And we do that by having an object we call the SOAP context. The SOAP context has a referral collection, it has a security collection, it has a path, and it has an attachments collection, and I'm probably even forgetting some of the other properties it has. The idea is that if I'm in ASMX or anywhere where I'm doing SOAP and I'm using the WSDK, I can create one of these contexts, or there may be one already available to me, and I can fill up these information items. I can fill them up with my security tokens. I can say, I want you to sign the message. I can say, here's a key to encrypt the message with, so on and so forth. Once it's filled up, we'll take that SOAP context and we'll modify the SOAP message on the way out. That modification may be all the way to encapsulating it within a DIME message with several DIME records. If you say, here are some attachments I want you to send to it. And then again, the same thing happens. We receive that message, and we're going to fill up these properties of a SOAP context to a message for you to read and to look at. For instance, then to do your own custom authentication, or to look at those attachments and put them into a file, some kind of file, or on disk, or wherever you think is the right place to put those things. And in fact, one of the things we'll do is, in both of these cases where our pipeline is running, we can call out to your custom code to do things like, help us, figure out the right security. If given a username, is this password a password you believe in? So on and so forth. And we also even allow you to write your own filters that do very, very similar things to what we do. I'm sorry, I'm not trying to laugh. Okay, there we go. So one of the things we offer, this is kind of a diagram that shows how the architecture works for the WSDK in the core processing pipeline. I figure we're all technological geeks here, so you'd just love to know. So if you're not off, I understand. But imagine you have user code here. This user code today probably just sends us out a message, and that's it. Whether that's using ASP.NET Web Services, .NET Remoting, just a DOM and an HTTP writer, that's what it does. What we've done is we've said, give us the SOAP message, give us that SOAP context object, we'll run it through our runtime, and we'll have our filters that do things like routing and security and DIME. Add your own custom filters for what you want to do to the message as well, and then we'll output a SOAP message in the end. This SOAP message will be different than this one. That's the idea. It's very straightforward. We host this. We've written code to host this inside of ASMX, inside of ASP.NET Web Services, both on the client side and the server side. We've also made sure that it's public for people who are doing things outside of that. And in fact, we have a HTTP handler that is non-ASMX based that we use for routing, so for people who want to implement routers. So our router grabs this and hosts it itself for messages that are incoming to it, so they can verify the right security tokens, so on and so forth. It's a very straightforward architecture, and it works quite well as long as you can get this context from user code to our runtime. Now, the opposite is just as easy and just as true. Given a SOAP message that comes off the wire, somebody has to be listening to it. We haven't written a listener in V1 by any means. You can host our runtime. We'll do things like unencapsulate, pull off security headers, so on and so forth. Run your own custom filters, and then we'll hand to you this code, which could be user code, could be an ASMX page, could be many things. We'll hand to you a SOAP object, which is different than this one. We've extracted a bunch of stuff off of it, and a SOAP context with all these various properties and so on and so forth. You can then take this, use it, do your own thing. We've tried to make it simple, straightforward, and easy to use in a lot of situations. So let's go ahead and try a demo to make this a little more straightforward.
Question?
Go ahead and ask a question while he helps me figure out how to switch to the laptop here. There's an AV guy somewhere, right? I guess not. Well, I'll figure out the... Go ahead and ask the question real fast while I'm doing this.
So both at the sending and the receiving end, should one be completely GXA compliant, or I can actually have a subset at the receiving end from the sending end?
So you're asking, do you need GXA compliance on both ends when you're using the WSDK? Is that what you're asking? You certainly don't need the WSDK on both ends, but many GXA specifications say when you send a header, add what's called a must understand attribute equal to true, or that's the recommendation. So that's what we do. Meaning, the other side, if it's a well-behaved SOAP endpoint and it receives a security header that says must understand equals true, and that endpoint doesn't have any code that understands that security header, it should send a fallback and not work. Now, you can certainly turn that off if you just want to add these things as a hint. So, for instance, and you'll see this in a second, when we send messages, by default, without you doing anything, we add a timestamp header that says when the message was created. There's no must understand equals true on that one, such that somebody who receives it and doesn't have the WSDK, doesn't have Apache code that understands timestamp, anything like that, they'll continue to work fine. But then if you add a security header, there'll be a must understand equals true. The other guy has to understand it. We are working with IBM, though, to make sure that we interoperate on all these GXA specs. So do you need .NET on both sides? Do you need this toolkit on both sides? No. For a lot of features, you need something on both sides. I believe you had a question, sir?
CF support?
Say again?
CF support?
Oh, the question's about CF support. So the .NET Compact Framework runs on cell phones, Windows CE, et cetera, and so on. It's a subset of the .NET Framework for PCs. Do we have support for it? Right now, no. We are actively investigating support, though, because it seems like there's a huge number of scenarios where the GXA makes a ton of sense, and there is web services support already on the Compact Framework. They're right above me in the building.
Supporters for putting it in, or?
Well, I mean, if we do, come up and tell me your name. And I think everybody believes it's a good idea. It's all a question of is it worth the resources for this fairly tactical product, or is it worth the resources for the strategic product? Is it worth it for both? When do customers need it now? So on and so forth. It's a really, really necessary thing. The GXA in general, SOAP in general, have been designed to work on devices like CF and PCs. I mean, there's not an issue there. I definitely want to see it happen. It's just a question of when, timing, and resources. If there's not other questions, we'll go through this demo. And the demo is really straightforward. We're going to take a V1 web service that does a stock quote, right? Very straightforward, and it does a portfolio. Give me the stocks I own and the number of the quantity of those stocks. We're going to add the WSDK. And automatically we're going to see a difference and a change that's going to occur. So here we have Visual Studio. We have my little form. I can get a quote. I can give my username, password, and get a portfolio, et cetera, and so on. And we have a web service, an ASMX page that this guy, and if we build and browse, you can see he can go to, just like the typical ASMX page. Now, I already have the WSDK installed. So what we're going to see that's different already than if the WSDK was not installed is this timestamp header has been added. So if we go ahead and hit F5, we're going to get our little WinForm to open up. And it's going to be exactly the same as always. We type in MSFT. We ask for a quote. This is just all local host. It's going to come back and tell us MSFT is selling at 120 a share, which would be nice. Of course, this is real. If we ask for Sun, it comes back with 5, which is also nice. And if we look here, I have a trace from the MS-SOAP toolkit. This trace of the request message is almost exactly similar, exactly the same as the trace you'd see without the WSDK, except we've added 2 headers. We've added a message times, and we've added a path header. We could take out both of these. We could say don't send either one. By default, we'll just automatically add them. And for response, the server also has the WSDK installed. So you can see he doesn't add a path header because he doesn't really have a reason to, but he does add a message times right away. Yes, please.
2 in the ID is gone now, right? So is that going to go in the May release? The question I asked earlier about WS routing, the 2.
Oh, the 2 in the ID. Yes.
ID
I'm
is
using a slightly older build where we did have the old versions of WS routing.
That is going to change then.
Yeah, that'll change. It'll be the new WS routing. So you can see we have these. Nothing's really semantically changed about the message much. If there was a referral cache, you can add a referral cache that says If you want to send a localhost / stock service, really send it to localhost / new stock service. We could add a configuration file, and that would happen automatically using WS referral and WS routing based semantics. So this is all very interesting and nice, but of course we can really go a little bit farther. And for this get quote, we could add, we could mess with the request context of the quote. So we can say service, this is the proxy class that is created for me when I use add web reference from Visual Studio or I use Wizzle.exe. So I can say service dot request SOAP context. And then this is for this service for all requests it makes. You can also attach this context to a single thread if you didn't want to use proxy classes. We could set the actor. We could add things to just a dictionary of name-value pairs. This could be used for custom filters that people want to write for samples of reliable messaging or transactions or things like that. We have a series of interesting information, such as the path. For message, there's a message times header. We could say message times dot expires, and we could say datetime dot now plus datetime dot. Let's see if I can do this right. Let's see. I want to do. Let's do date. Actually, we'll just say it expires right now. I think that might be kind of interesting. If I wrote this code right, which I didn't, that expires dot. There you go. Let's just add. Let me do this again real fast. This is the one piece of the demo I didn't think about doing. Let's just add something to the path so I don't have to worry about what I'm doing. So we'll add to the path. Actually, the best thing to add to the path is to modify the must understand. By default, the must understand is true. We can certainly make the must understand false. And that's a straightforward kind of activity. And now if we ask for MSFT, we get back 120. And if we look at the message, see the path, we've taken out the must understand equals true. Those kinds of things, we mess with that object model, and we can change whatever we want here. I don't know why I'm freezing my brain on how to expire the message, but you can certainly see the idea there. If we go back to, I believe, the slide presentation, we can add, we can talk about the security programming model, and then I'll show you a demo of that. With the security programming model, we have in that SOAP context a security collection called security, where you add SOAP security headers. For a SOAP message, you can imagine you're going to be sending the SOAP message from the initial sender to your firewall, and then to another firewall on the other, for your business partner, and then finally to the receiving service. There are two intermediaries in that situation, and a final destination. You may want to add security headers for all three of those. So we've made this a collection where you create a security header. If you don't say who the actor for that security header is, we just assume it's for the final destination. But then you can add tokens, like security tokens, X509 certificates, username password pairs, or you can say I want you to encrypt pieces of the message and add the encryption data to this header as well. And then you just add that to the context. Either that SOAP context, and we'll do all the right cryptography in the message for you. So we'll take our previous demo, we'll add a username token, and then we'll actually add a X509 token to the message. We'll add a username token for get quote, because you can imagine we in a scenario where you only want to return stock quotes for users who are authorized. Then for the get portfolio, we'll add an X509 certificate. And on the server side, we'll read that X509 certificate, decide if we want to trust this person, and then we'll encrypt the message with that public key that's in the certificate back to the user, so only he could even read it, which is a fairly straightforward operation and often done. And somehow I didn't do something quite right. All right, here we go. We have the demo back up. So what we'll do, first off, here's our client still. I have some code I'll just drag over where we add a username token. So we create a security header. Then we create a username token. This username token is created with a username, a password, and then a password option. We can send the password SHA-1 hashed, as WSecurity provides for. We can send it plain text, assuming you're going to use SSL or some other encryption format. Or we can actually not send the password at all, and then you can create a signature based on the password, such that we send the username and then we sign the message, which is actually a nice, secure way of sending passwords as well, or getting password information across. After we create that username token, for the security header, in the tokens collection, we add the username token, and then we add to the request SOAP context security collection our new security header. This is all the code we have to add, and now this username password pair will appear in the SOAP message. So let's ask for MSFT. It'll load. The server side will be fine with that and close things down. And if we look at the SOAP message itself, we can see we have path, we have a message times, and we also have a security header with a username token and a password, which is SHA-1 hashed, and we indicate that with password digest. So everything just kind of works. It's very natural. And you can actually, if you want to, write what we call a password provider that implements an interface, register that in config, and then we will go to your password provider, and you can hook that up to your custom database of username passwords or whatever you have, which a lot of our customers have, and we can then actually check this hash of a password, so on and so forth. That works pretty straightforward. If we want, we can also, for this Git portfolio, as I mentioned before, we can add an X509 certificate. It's a little bit more code. We can look at it and see it's pretty straightforward. We've added APIs to actually open up an X509 certificate store. Within that store, we can say, open it for reading, and then we can pull a certificate out, and we actually allow you to create a UI, a select certificate UI, where you give it the Windows handle. That works great for Windows apps. Create your security header, just like we did before. Create a security token, an X509 security token, based on that X509 certificate. Add that to the collection. Now you can create a signature object, just as easily, give it that same token, and add it to what we call the elements collection. This elements collection is used both for signatures and encryption data. Add that security header to the request SOAP context. Again, that's all you have to do. It's about, it's a few lines of code, and you have an X509 certificate occurring. So now, when we say Git portfolio, we have a windowing API to select a certificate out of the store. I have a single certificate in there. I can choose that, sends it to the server. The server is going to not do anything, in fact, at this point. It's up to the user code to authorize this person based on that certificate, although we will extract the certificate out and verify the certificate is cryptographically, X509 certificates are signed and whatnot. We verify all of that. We can also verify trust chains, et cetera, and so on. We do those pieces for you. We don't do complete authentication for you. And here we see a common portfolio. And now we go to the server side. This is just a normal ASMX. And we can go to this portfolio, Git portfolio. And this is your normal web method. And if we want to, in the toolbox, we can actually grab that same security token from the response context. We can grab that security token. So we're going to take the token that we extracted out of the message, that was the user's token who sent the message. We'll pull that out, and we'll create what we call an encrypted data object based on that token. We'll add that to our security header, and we'll add that security header to the response context from the ASMX. From here on out, it's just normal code. Just whatever kind of business code you have. But if you run it, we'll see a pretty big difference in that now from the user's perspective, the only thing that's changed is we're still selecting a certificate. You could even do that programmatically, and the user doesn't need to notice that. And we get back our portfolio. But if we look at it, if we look at the message trace, we can see here there's a security header with an X509 certificate that's base64 encoded, and a signature has been added based on XML digital signatures. We indicate the XPath of what is used for the signature, and then we say get the portfolio, and then the SOAP toolkit sometimes has a bug where it doesn't display the source for you correctly. So here we can see an envelope where we add a encrypted key object, as XML encryption discusses, in the security header for the response. We say, hey, here's the key name, and you can see the key name looks like what you'd find for an X509 certificate. We give cipher data. And then if we look at the body is encrypted. The body no longer says what your portfolio is, yet it's all message-based. So it's not SSL. No one can read this data from point to point. It can only be read end to end, which is kind of the point of WS security. So we'll go back to the slide presentation. There's a lot of other security things you can do. This is just one. Yes, please.
How does a session key get negotiated if authentication doesn't have public keys available?
The question is, how does session keys get negotiated? I'm not sure what you meant by the second piece, with public keys not available or not.
If the authentication that the server uses is not based on a public key system, like it's using Kerberos or
I see. So if a server wants to use symmetric keys.
Yes.
So the way we actually work is we have an interface called decryption resolver, and by default we can do decryption. We'll call our own decryption resolver for X509 certificates. We plug that code in. However, you can register and configure your own decryption resolver, where we give you the key name that we found in that key name section of XML encryption, and then you give us back the key to use to decrypt. And on the client side, you don't need to add anything. You just create an encrypted data object, and you can create that instead of with a token. You can create that with a symmetric key, and then we'll encrypt on the way out with that. And you can also create a symmetric key piece for that. We don't do negotiation. That's not a feature we want to do in V1 because we felt it would take too long, and because WS Secure Conversation is the spec that describes how to do that kind of negotiation over SOAP, and that's not published yet. So we will have a sample. Hopefully that sample will have security conversation out in public by then, such that the sample will show you how to do that. Where to begin with, you'll ask for a public key, then you negotiate down just like you do with many other programs. But we give you the right hooks, which is kind of our philosophy. Let's give you lots of hooks to plug things in, but we won't offer every feature. So a lot of other things are possible like that. You can also use, we also support custom binary tokens. WS Security supports both Kerberos and X509 certificates as what it calls binary security tokens. We allow you to create your own custom binary security tokens. And already we have early customers who've asked for this because they're going to create their own binary blobs that they're going to sign for their own security token types. And so we support all that with security in general. It's, like I said, it's a very just kind of flexible structure. All right, we're kind of at the Q&A point. My contact info, I'm Keith BA, is my alias. If you go to XWS, there's a WS Dev Kit link to learn more about the development kit. We're ending a little early, so you can ask more questions. This slide presentation is off of here. If you go to the WS Dev Kit link, there's a link to this presentation. All the samples I've shown you are in the MSI for the Dev Kit, which we hope to, like I said, have public before the beta, hopefully in the month of July. I have backup slides in this presentation that we can discuss as well, if you want to discuss DIME or something like that. Otherwise, I'd be happy to hear your questions, or we want to get out a little early since it's Friday. Feel free. It's very sunny outside. So we'll start with you, Peter.
When you read the subheaders, you just take the whole XML and put it in a DOM?
Yes. In fact,
and then you reconstruct it.
Yeah. In fact, we're not the fastest thing around because we do take the entire SOAP message and put it to a DOM, and we do that because we're considering the security features to be Pri 1, and that we're assuming people will always want to do the security stuff, like sign a message. And unfortunately, to sign a message with the .NET framework always requires a DOM because of the way XML signature, the specification was written. So we DOM things up, and if you want to write a custom filter to do your own thing, like if you wanted to implement WS foobar with the dev kit, you could write a custom filter to do that. You could pass information in and out with that SOAP context. What we'll give you is a SOAP envelope object that looks very, very similar to, it's actually a subclass of DOM with a bunch of added properties and methods on it.
So will you ever get confused with, so the headers, you just look at the ones with your namespace and ignore them?
We look for the ones that have, we know whether we're running in the context of an intermediary, whether we're an intermediary or whether we're an endpoint, and we know the actor name, because we assume actor name is the request URI, the actual physical request URI. So assuming we get a header with the request URI as the actor name, or none, and we aren't an intermediary, we strip those headers such that they're understood. Ones that have a different actor name that we don't recognize, we pass on through. We just give up to the user code or the intermediary, which can send it on, that kind of thing. Other questions people might have? Yes, please.
You looked at the costing for a CF port? Well, how much code is there, what you've done? And
you're really into the CF thing.
Yeah.
We've just started investigating it. I had a meeting last week with the CF team. We're going to have another meeting next week where we go into even more detail. It's certainly not impossible. How much is what?
What's the size of your team?
Our team's small. Our team is not the size, like Message Bus is much, much larger than we are. It's not even so much that as there's this cost. Anytime you want to port to CF, and I was the PM for ASP.NET Web Services, so we had a kind of a similar exercise then. Your biggest cost is actually, trying things out, running them, doing QA, and then finding out what fails because that resource, that type of API, doesn't exist on the CF platform. And then you have different levels of CF platforms, and you have to figure out, which ones are you going to support. And the most interesting difficulty that we're going to run into is we don't just use the .NET framework. We actually have to make some calls directly to the crypto API in Windows to do some of XML signature and encryption. So that itself, how much of that's available in CF, we're doing that investigation. We should know soon. And definitely give me your name so I can let you know how that goes. And in fact, we're looking for testers, as Oliver mentioned, for the Indigo team in general. And certainly the more testers we have, the easier that kind of thing becomes. So if you know testers, let them know. We're looking for them. Other questions people have, be happy to answer them. My email address is KeithBA, KEITHBA. Yes?
Where can we get the drops?
Drops aren't out yet. We're hoping to have drops in July. But at the very least, we'll get them at the end of August when we go beta. And we're just looking at how to best get drops out internally so as not to randomize the team or give everybody internally bad drops that don't have the right documentation or samples behind them. So we're in July, sometime this month. I really, really hope to get drops out to people. I can't guarantee it yet. So are there no other questions? Thank you for staying. It was nice talking to you.